went to high school in Milltown, Wisconsin, and the last time I visited there, I found the school that I'd gone to had been torn down and turned into a parking lot. I got a bachelor's degree at the University of Wisconsin in Madison. At that time, there was only one University of Wisconsin. The place where I stayed there has also been torn down, but the school is still going strong. I graduated from Wisconsin with a bachelor's degree in chemistry just about the time the draft is being started, but it hadn't gotten to be with a great pressure on people to be drafted, but I did get a job working in the oil industry in East Chicago. And there we were just starting out on catalytic cracking. And at that time, catalytic cracking was very important because it was the only way to make large quantities of aviation quality gasoline. So I spent the war years, this was the Second World War, not the first, the war years, working on catalytic cracking and making aviation gasoline. During this time, I took night courses at the University of Chicago with the idea of becoming an organic chemist. But some of my colleagues at Sinclair said that if I would go to Northwestern and work with Professor Selwood, they would see that Sinclair set up an industrial fellowship. So I went to Northwestern and with the fellowship to grease the way, I was accepted at Northwestern and started working for Selwood on doing magnetic studies. The important thing that I really learned there was that there are good professors and poor professors, and that Selwood was one of the very best. And I appreciated the way that he steered us towards productive work, but never gave the impression that we were just doing what he wanted done. After I got my PhD, it turned out that Sinclair, which had been paying for my education, had no interest in basic catalysis work. And they offered me a job to do pilot plant Fischer-Tropsch work, which didn't appeal to me. So instead I took a job at Texaco in Beacon, New York, which was setting up a basic group in catalysis. And it is there that I worked for 25 years, with most of the effort being done on the infrared. But the first work I did involved isotopic exchange involving carbon monoxide on metals and amines on cracking catalysts. And I had come to a Gordon conference and heard many of the old experts, the type that Burt should have on his old fogey camera here, if they had invented this type of camera in those days. But the hot discussion was whether cracking catalysts, the acidity, everyone agreed these were strong acids and it was a carbonium ion mechanism. And the discussion was whether it was Lewis acid or Bronsted acid. And I knew little about infrared, but I had the idea that if these bases that I was absorbing on the catalyst, that if you absorbed ammonia and there was a proton there, that would become NH4, and if it were on a Lewis site, it would remain as NH3. And you could look in the reference manuals and see that you could tell the difference between NH3 and NH4 by infrared. So I went to a young man named James Mapes, who was working with infrared, and I told him this: we should try to see if we could tell the difference between NH3 and NH4 with infrared. And we did this and found that if we kept the catalyst as dry as we could, that the ammonia was present in the NH3 form. But even the slightest exposure to atmosphere converted it to NH4 plus. So our work provided a means of telling whether a catalyst was a Lewis acid or a Bronsted acid, but it really didn't prove which form was the active form in catalysis. When this major success, I will say, because it was actually in the most important field that we worked on, and that is in the field of cracking catalyst. When this worked, then I decided to try metals. Now, Jim Mapes, who had worked with me first, had a bachelor's degree in agriculture, and he felt that he could do better with this degree at some other place than Texaco, so he had left. And he and I delayed about a year in writing a paper on this chemisorbed ammonia. In retrospect, when you see how fast people publish things now, I often wonder how we were able to let this sit around for so many months. But what happened, I'd write a version, I'd give it to Mapes, who worked at a different company by then. He'd rewrite it, then I'd make some changes. And neither of us were in any great hurry about it. The atmosphere at Texaco did not encourage publication, and we had more or less to convince the people that it was absolutely worthless to the company before we were allowed to publish it. But as I said, the success with this started my attempts to try to see supported metals. Now, with infrared knowledge limited to familiarity with Beer's law, you could calculate that you could see the carbon monoxide which will absorb on a supported metal if the carbon monoxide had the same extinction coefficient as carbon monoxide in metal carbonyls. You probably could not see this carbon monoxide if the extinction coefficient was equivalent to that of a gaseous carbon monoxide, which is about 50 times less. So I started out with the work, and since Texaco at that time was working in Fischer-Tropsch, the CO and iron system was the one that I was familiar with, and I tried to see the spectra of CO and iron, and we tried for months without any real success. And looking back, it was due to the fact that we could not properly reduce the iron on the supports. And our previous experience had been with unsupported iron, which reduces quite easily. Well, I was allowed to work for several months without any result worth speaking about with the iron. And the supervisor finally asked me the question. He said, now, would there be any interest to catalytic people if you could see the infrared spectra of gases absorbed on metals? And I assured him that there would be of interest, and then he says, well, go ahead, keep working. But this sort of sent the signal to me when they start asking questions like that, and I stopped working on iron and went over to platinum, and the first effort with platinum produced gigantic bands, and history showed that it's easier to get a spectrum of carbon monoxide on platinum than it is to get a spectrum of platinum that isn't contaminated with carbon monoxide. And then we started other metals and led to the work which was published in the literature over this period of 25 years. Now the man who was our supervisor during this time, his name was Race, L.C. Race, R-O-E-S-S, was a physicist, electrical engineer person. He was an expert instrumentation man, but he didn't have any background in catalysis. He never interfered with what we were doing. But he had, before I'd gotten there, had made some important developments in infrared instrumentation. And the infrared spectrometer that I inherited from Mapes was Perkin-Elmer's third commercial instrument, the number 3. And when these instruments were sold, the infrared spectrum was recorded on a film, photographic film. And Race was the one who developed the technique of using a chopper so the infrared beam would be alternating and could be amplified by alternating current methods, and you could put it on a chart paper. And this turns out to be one of the most important advances in infrared instrumentation. And he had also made some other improvements. In one of them, you'd run the background and then roll the paper back and absorb the gas on the catalyst, and the operator would follow the background with a stylus, and this would have the effect of separating out the background logarithmically so that it did not change the absorbance of the bands as it subtracted the background. And in effect, this is what computers do, except we had a human being there to operate the stylus. Well, with these improvements, he had ended up with an instrument which was just ideally suited for the studies that we were trying to do. And we did have some sampling troubles, and which basically comes from the fact that using transmission through these solids, we would get about 5% transmission. And in order to even get this much, we had to use small particles of catalyst. And at that time, what turned out to be the most helpful assist from the outside came from the fact that Texaco was supporting a project at Columbia where a man interested in minerals was doing infrared of minerals. And he had a recipe where you'd grind up the mineral, sediment it overnight, take the top layers, and you'd end up with small enough particles that you wouldn't lose too much of the light by reflection. So we would treat our catalysts by the same procedure. And if we had tried to do our work without this procedure, we never would have been successful at all. There was not any catalyst literature that we were aware of, at least, on infrared when we started. So to my knowledge, this use of ammonia to determine whether it's Lewis or protonic acid was the first attempt to use infrared to settle a problem of catalytic interest. However, the people in mineralogy had been using infrared for a long time and looking at hydroxyl groups on surfaces. And you can go back to the very first infrared work by Koblenz, and he was looking at infrared spectra of hydroxyls on the surface of minerals. And it was somewhat of a mystery why catalysis people had not made more of an effort to do infrared when the mineral people were using it so often. sedimentation procedure was a very slow one, and I had gone to a lecture and heard a man describe a new type of silica which was made by burning silica and burning silicon chloride, and this produced a silica that had small round particles but had high surface area. So I went to see if I could find some of this material to use as a support rather than going through the sedimentation procedure, and I found a material in the grease department that they were using for thickening grease, and they said this is the same type of thing. It had a different name, which I think was Cabasil. So that's how we started using Cabasil, which was again one of the cornerstones of the success of the method, because Cabasil is the most inert support that you can find as far as its interaction with the metals that are supported on it. After the first successful run with platinum supported on the silica, which made us extremely happy because these bands were very big, there was no question about them at all, we set out to just reproduce the thing, and on the second sample we couldn't even push the infrared beam through the catalyst. It was just black, and this was of course very disappointing. Looking at it from this time it doesn't seem so bad, but when we were looking at it from the other side of the picture, it appeared to be extremely serious. And what the trouble was is I had written instructions to the technician that he should put this catalyst in and he should reduce it in flowing hydrogen at 350 degrees. And the first time he had raised the sample to 350 degrees and started the hydrogen flowing. The second unsuccessful time, he had started the hydrogen flowing at room temperature and raised the thing to 350 degrees. And when he did this, the platinum reduced while it was still wet, and large chunks of platinum were deposited rather than getting small particles. Now in the samples we had so much metal that you could not reasonably expect the infrared beam to go through them if you looked at the absorptivities of the metals. And it's only when you work with small particles which do not have metallic conductive properties that the infrared beam can get through. So that when we accidentally made very large particles, the beam didn't go through. Well, after we solved this, the things went very well, and we had no problems, and we worked on anything that we desired. Now, Race, who was the supervisor during this time, was an exceptional leader in that he would ask very penetrating questions. He had the best attention span of any man that I've ever encountered in my life. He could hear a lecture on almost any topic and ask critical questions at the end. And he had this group of young people like myself. There were about 10 of us working on various aspects of basic research related to the petroleum industry. Each week we would have a meeting, tell what we had done during that week, and we would question each other. So by the time we really had something done, it had been gone through a lot of very pertinent questioning. And as I look back, this group that we had at Texaco and similar groups of catalyst people and other oil companies were far superior to any catalysis group that I know of that exists in the United States today. Each of the oil companies had these groups of basic catalysis people because catalysis was brand new. Most academic schools had never heard of it, didn't have any serious interest in it, and about the only schools in the country that had any contribution to catalysis were primarily Northwestern, where Pines, Burwell, and Selwood and Apatia were there. And there was some one-man activity at Princeton under Hugh Taylor. But most academic people just had no concept of the importance of catalysis. And as a result, the basic work was done in industrial laboratories. And to my mind, this is the best place to do it if you have an atmosphere that lets it go on for a long period of time. Unfortunately, each time there is a change in management, you're likely to get a change in policy and basic research. But at Texaco, we continued for 25 years, mainly due to the influence of race, who had the complete confidence of the people above him. Right now, I don't intend to go into the details of the various studies we made with hydrocarbons, hydrogen, nitrogen, adsorbed, and so on. And we could, as the thing developed, as the infrared developed, and the company could see people were coming from all over the world to see the thing that we were doing, that this outside interest gave us a lot of prestige within the company, and as a result, I had essentially a free hand in deciding what would be worked on, what wouldn't be worked on. Many times we would try something that would only be partially successful, so I'd take and put it in a file cabinet and work on something that was easier. But due to the fact that there was a negative pressure on publications, we were very cautious in asking for papers to be published, and we usually wouldn't make this request unless there was an international meeting which involved a good trip to Paris or Amsterdam or someplace like that, and then we would get a paper ready for it. And if we were writing a review paper, we would fill it filled of material which could be papers by themselves, but which were much easier to get through Texaco if we just included it as part of a review paper. So most of our work on absorption of hydrocarbons is in review papers, not in primary publications. Okay, Burt, ask a question.
How did you look for a job in 1940? What was the procedure of getting out of college then?
In 1940, as I remember it, just some professor said, Sinclair is expanding. At that time, I had no experience in catalysis at the bachelor level, but someone said Sinclair's expanding, and essentially I got the job just by writing them a letter and sending in the resume or whatever it was. And it wasn't that the grades or anything were so good, it was just that they decided they were going to hire about 24 people at the bachelor's level, so that anyone who had a bachelor's degree from a decent school was hired. And in those days, when I started at Sinclair, technicians were not known or not well known, so that these people they hired at the bachelor's level did essentially what technicians do now. In the first year, I worked on shift work running pilot plants and catalytic cracking and things of that nature. There was no personal interview, and that's how I happened to work for Sinclair.
And by the time you got your PhD...
At the time I got my PhD, I first talked to Sinclair, since I wanted to go back there, but they had completely revised their concept of catalysis, and as I said before, they wanted me to work on Fischer-Tropsch as more like an engineer would work on a pilot plant type of thing. And at Northwestern, I had become imbued with this concept that basic research was the thing, and I wanted to do basic research, and Texaco had sent a representative to the school, and I told him what I wanted, gave him my resume, and again I was hired without meeting the people I was going to work with. It was sort of just on the basis of the initial interview, and I had never been to Beacon before I went there for my first day's work.
Well, for a company to give money for an employee to go back to school seems unusual. Was this a special case, or did Sinclair...
Well, this was the first time, but in those days they did companies, there was far less government support of work, and companies did put more emphasis on industrial fellowships. And this fellowship that Sinclair started with me as the first one, was continued after I left, and went on until Selwood left Northwestern about 20 years later.
Was this because of a special relationship?
I think it was because of the special relation with Selwood, which involved contacts within Sinclair that I didn't know anything about, but there were people at Sinclair that were interested in his magnetic studies of catalysts.
And your selection was because you knew the right person, or?
Well, it certainly is because I knew the right person, whose name is Bob Van Noordstrand, who was one of my co-workers at Sinclair, and he was the one who put the whole idea in my head of, why don't you go and talk to Selwood, and he was going to talk to the people at Sinclair, and that's how it came about. It did not, I don't think, imply that Sinclair really thought that I was such a bargain, but rather these people did have a high regard for what Selwood was trying to do.
What sort of interaction was there between Selwood and the other people in catalysis at Northwestern?
At my level, I didn't get into really the nitty-gritty. Some years later, it was my impression that the interaction wasn't quite as smooth as it should be. Herman Pine's laboratory was next door to ours. Herman had no faith in what was called catalyst characterization by physical methods, which was what I was doing with the magnet. Burwell and Selwood were about the same age, and I now recognize that there was some sharp questioning between them at various seminars that their students had to present. But as far as I know, there was not any tremendous amount of interaction, and that Burwell and Pines and Selwood all sort of worked independently. Now, Epodieff was at Northwestern at the time, and he had been on the right side in the Russian Revolution, but that turned out to be the losing side. So he wanted to come to this country, and they wouldn't, and it was UOP now called Allied Signal, that wanted to bring a Podieff in, but for reasons I don't know, that an industrial company couldn't bring him in, but he could be brought in as a professor. So there was some arrangements made with Northwestern that he would spend part-time at Northwestern and part-time at UOP. And at UOP, of course, he did some of the most important development of which Herman Pines was sort of his second in command, but he made this very important developments in alkylation, catalysis, and things of this nature. And the Podieff would come to the school very often, and he was always quite friendly with the students and so on. And I think persons such as myself really didn't grasp the importance that he was really one of the fathers of catalysis. That we didn't quite realize this until we long graduated and saw how he was considered in the outside world.
How did you, Selwood become interested in magnetization? Are you aware of that?
He had done some magnetic work at Princeton as part of his, or perhaps a major part of his doctoral or postdoc work. Exactly how he got into catalysis, I'm not certain. And he did not have a great deal of experience in catalysis when I got there, and in many things dealing with catalysts, the fact that I had worked in the petroleum industry for 4 years, I really knew more about how catalysts were made and so on than he did. But how he actually got into the catalysis field, I do not know. But he certainly made some very important contributions in that area.
Well, I always admired the way he handled controversies among two reviewers. He would sit down and read the paper and then tell you what he had decided. Was that typical of his personality?
No, I'll tell you, Selwood is now gone. To his students, he was the nicest fellow you could imagine. The other students at the school didn't like him very much because he would walk down the hall and he would be immersed in his thoughts and he would not...
Oops, excuse me. Were you in? I didn't think you were.
That he would not recognize the students and even say hello, so they considered him to be stuck up and so on. But to his own students, he didn't seem that way at all, and his office was right next to the lab, and he would come in and do laboratory work on his own. And this would be things where he was being paid as a consultant, but he would do the work himself usually.
Well, did he maintain contact with Taylor after he got to
I would say not in any significant way where they would discuss each other's work. Their only contact would be like coming to the Gordon conference and meetings of this type. Now Taylor, I had some contact with, and although he was a great contributor to catalysis, he never had a very high regard for infrared. And I remember a meeting at Princeton which was supposed to get the industrial and academic people together in catalysis. And Taylor made the statement that there had never been any significant basic work in catalysis done in industry. And a fellow from Gulf says, well, how can you say that? What about this infrared work that Eischens is doing at Texaco? And Taylor said, that's nothing but engineering. And all my life I've been wondering, what on earth did that statement mean?
Well, now, did Burwell and Taylor keep in contact after Burwell got to Northwestern?
I don't know. Both Burwell and Selwood had worked with Taylor at Princeton, but when Burwell started at Northwestern, he was just a young junior faculty man at the time that I was there. Just fresh out of getting his postdoc. And what he did with Taylor, I don't know.
Well, Northwestern also had people working on kinetics that were on the faculty. Did they interact with catalysis, or was
I would say no. To my knowledge, no. The other people in chemistry that, well, there's Farrington Daniels, who is well known as a physical chemist, and people still are rewriting his textbook in physical chemistry. But I'm sorry, I made a mistake there. That was Wisconsin. But
yeah, Froster, Pearson.
yeah, Pearson was a young man who really associated more with the organic chemists and had very little association with us. Now, I'll tell you, in schools they can talk about this association all they want, but in almost every case the professors are little empires unto themselves, and there's very little interaction between them. So being in physical chemistry laboratories in the basement, we had little interaction with the organic chemists who were up on the second floor.
Well, Selwood sounds a little like a person who was somewhat of a perfectionist. Is this true? Or?
I didn't notice it in that he was putting any demands on us to do the work. He certainly was careful and honest, but he was also, I would say, the best speaker that I've ever encountered as far as presenting a technical talk, and in these days you'd expect a person with his talent as a speaker to be an anchor man on one of the major broadcasting networks, because he was a really superior speaker.
Why didn't you continue in magnetism when you went to Texaco? This is a normal course for someone to try to follow what they did.
Well, first, when I went to Texaco, they didn't have any magnet. I didn't particularly want to continue it. What Race did is he just let me browse around for a month or so, and then said, what do you want to work on? And at that time, one of the fad problems was whether the surfaces of catalysts were uniform or heterogeneous. And the fact that they appeared heterogeneous came from the change of heat of adsorption with coverage and things of this nature, which were rather unsolid bits of evidence, because you could visualize a situation where a surface could be homogeneous, but just by the fact that it was half covered, it would be chemically altered. So I had the idea that I will determine whether a surface is heterogeneous or homogeneous by exchange. Instead of varying the surface coverage, I'll completely cover the surface with carbon monoxide, and then I'll see how fast it exchanges with radioactive carbon monoxide.
Was this before or after Emmett's work on that?
This was before. And I found that there were 3 distinct rates of exchange, and that these surfaces then were heterogeneous. About that time, again, and we were usually couple of years behind publication and getting the work done. By the time I got ready to publish, Emmett had published a paper involving exchange, and there was no question whose work got the attention then.
Well, in holding up publications, one might perceive the type of person who is somewhat of a perfectionist in wanting the results to be very careful and correct. Was that your case?
I don't know that I can make that claim. It just, there was no pressure to publish. And to publish something was sort of a nuisance. And it wasn't that we didn't decide to publish, but we never had this pressure that we'd better get out there and be first, or else someone else will publish the same thing and they'll get all the credit, and we wouldn't get tenure. Our jobs did not depend on the number of publications. In fact, I'm sure the higher up people in Texaco thought that we were there to make practical contributions to their catalysis work, and that a few of them, like Race and the manager of the laboratory, had a good grasp of what you could expect from basic work, and but I'm sure that the higher levels of the company didn't look at it the same way Race did.
So it sounds as though you were practicing research for research's sake even better than in a university.
We were working on research for research's sake, and because of Race's ability and his strong personality, there was never any doubt.
Hey, Burt, how you doing? Excuse me. I'm sorry. Am I walking in? Oh, you.
Because of Race's personality, there was never any doubt who was the boss. But he protected us from the people above, and they essentially gave him a free hand because they trusted his judgment, and he sort of had them buffaloed. But we just never had the same pressure to publish something that the people seem to have nowadays. That were your job, your proposals, and I'll tell you, as a person who worked where proposals are evaluated, the number of publications counts. No matter how they might protest that it's quality or some such thing as this, it's the number of publications which is the important thing when it comes to getting proposals funded and so on. But we did not have that pressure at all.
In a 2-year period, you published 3 or 4 papers on carbon monoxide, which have not been altered at all today, where you showed where the carbon was attached to the metal. You defined with carbon-13 isotopes a lot of...
Well, this is correct, but the basic thing in all of our interpretation was that we would compare spectra from surface species with spectra of compounds of known structure. When we first did the infrared work on carbon monoxide, the metal carbonyls would be the thing that we would compare with. And fortunately, there were only 2 or 3 carbonyl publications in the literature. So it was very simple that we could see that the carbonyls that only had the linear COs had bands above 2000, and those like the Fe2CO9 that had bridged COs had bands below 2000. So that's how we interpreted it, and we didn't really take that interpretation as very important. How else would you interpret it?
Well, now, when you did the CO exchange with isotopes, was this carbon-13 or 14?
Well, the one I was talking about, that was 14. That was radioactive studies.
Did you set up the initial facilities there, or were they existing?
Well, carbon-14 is a very weak thing, and you could buy carbon-14 compounds. I had to make a Geiger counter which had a window thin enough so that the carbon-14 rays could go through it, and this window had to be strong enough to withstand vacuum and so on. And there was a paper by Kummer and Emmett where they had made a gas counter of this type, so we just copied theirs. And this worked all right, but to show the type of facilities, sometimes the background on the counter would go up to enormous levels. And this was very puzzling until I discovered that the man who had the x-ray machine in the adjacent room would be changing the position of the lead bars that he was using as shielding, and if he'd get them in the right position, they would just come through the wall and hit my Geiger counter. So with the infrared, you'd use carbon-13, but for the exchange work, we'd use the carbon-14.
Now, Mitchell was working on carbon-14 tracers and hydrocarbon about that time. Did you interact with them?
Yes, yes. John Mitchell was one of the members of our group, and we interacted a great deal with him. He was one of the older persons, in that he had been in the group 3 or 4 years or so by the time I had gotten there. And he had been sent to Oak Ridge or some such place to become an expert in radioactive studies. But I'll tell you, the main interaction that we got was that I got. First, when Mapes left, he was replaced by 2 infrared people. One was Stan Francis and one was Bill Pliskin. And these were 2 people that were real experts in infrared. They didn't know a thing about catalysis, but they were extremely well trained in infrared. And at that time, the oil industry was interested in using infrared to analyze hydrocarbon mixtures. And that's what Stan Francis was doing, and he was working on a homemade infrared equipment to do this. Pliskin had gotten a degree in theoretical infrared. He had not worked in the lab at all to get his degree, but it turned out that their background was just exactly what was needed to complement my catalysis and no infrared type of background. So we got along very well. At a time, there was a time that Francis split off to do reflection infrared, and Pliskin and I continued for many years to do the transmission catalysis infrared. And when you look back at the work that Francis did in reflection infrared, he clearly outlined most of the factors that are involved in reflection infrared that people think are rather recent discoveries, such as using determining what bond angle, whether the thing is perpendicular to the surface, horizontal with the surface, and so on. Francis had a very clear idea of all this and did some very beautiful experiments which outlined that the infrared experiments agreed with the theory.
Well, how does one feel having seen this work repeated over and over again over 30 years without very much advance beyond where it was 30 years ago? Is this frustrating?
Well, no, it isn't frustrating. One of the things was that we were, because of race, because of our other colleagues, and because of Pliskin's personality and my personality, we were very careful on what we published. And usually, if I could convince Pliskin of something, or he could convince me of something, it was difficult for outsiders to to second guess us. And we did make a large number of mistakes. This infrared seems simple, but you can make mistakes very, very easily, and we made many mistakes, but fortunately we caught most of them before they were published. But then, as the years went by, we would see our mistakes published by other people. And because of this, we would criticize these others who had repeated our mistakes but had published the errors. And people sort of thought that we were pretty grumpy, I guess, looking for errors that other people made, when really we recognized their errors because we had made the same ones.
Well, when you worked on platinum, had the platinum reforming catalyst been introduced?
It was just about the time that it was introduced. I don't think that we worked on platinum because of its importance as a reforming catalyst, because we started out working on silica-supported platinum. But it was about that same time that platinum reforming catalysts were introduced that we started working on platinum.
I take it that Ross would have supported you if you had chosen another area as an infrared, even though he had worked on that.
You mean race?
Yes.
Yes, as I said, I don't know whether I got off the story or not, but he gave me about a month to decide what to do, and I finally said I want to do these exchange experiments to see whether surfaces are homogeneous or heterogeneous. And I told him not much more than I'm telling you now. He said, go ahead, and that was it. That as long as I found something that would answer a substantial question, that was it. And then I drifted away from that only because the infrared, the first experiments with infrared looked successful, and it was much more attractive than the exchange work.
Outside of your own research group, how many people in Texaco followed the work of these 10 people working on rather fundamental projects?
Very few. Some of the work, especially the work that Francis did, was aimed at lubrication studies. Francis was an excellent researcher, but he did not like to give talks in public. And as a result, he would do his work, he would publish the paper, and that was it. These days it seems that you have to publish, talk about the same thing time after time if you want anybody to pay any attention to it. It was for that reason some of the major contributions that Francis made were just sort of lost because he never went out in the world and publicized them.
Well, I assume that the carbon-14 tracer studies you did with carbon monoxide had some different aspects than what Emmett found. Today, one would normally publish that.
Yes, mine did. Actually, Emmett's, with due credit to him, I don't think that Emmett sat down and said, this is a problem we can solve with tracer work. But he was interested in carbon monoxide on metals, and he did find that the exchange between the adsorbed and the gas just took place. See, my argument was that it's going to be much easier to get an exchange than it is to desorb a molecule of CO, because in the exchange you just trade one for the other, and it's going to go at room temperature. I did not see in Emmett's publications that he was really intent on using the exchange for any specific problem, but rather just to see whether it went or not.
What was, during this period, the typical number of people that you would have working for you? Technicians, BS, etc.?
All right, we would, for the most part, I never had more than 1 or 2 PhDs working with me. That's during my entire career at Texaco, and I mean working with me on the infrared. And we would ordinarily have 2 technicians. These would be people who had gone to high school but did not have any formal training. You would write out what they were supposed to do in the morning, what runs they were supposed to do. You could depend on them doing it according to the directions that you wrote down. As I illustrated before, in the case of the reduction of platinum, there'd be errors, but these would be errors where the instructions hadn't been quite as clear as they should have been. And I remember one of our technicians who never got the concept of vacuums. So he would always be talking about, we finally got to him, would say, fill the system with a vacuum. That's when we wanted him to pump it out, because that was a language he could understand.
What do you remember about the first Gordon conference you attended,
Well, that's
other than the infrared?
Well, I was very impressed by these overweight people who tended to sit in front and seemed to have a tremendous background and know a great deal about a wide variety of things. And these were people whose names I'd heard. But I it was just like the people that sit in the back now, I assume.
And who were some of these people who sat in the front row?
Well, it was H.S. Taylor and Kamereski and von Grossa from Temple, who argued that carbon on cracking catalyst was really the catalyst. And this concept of the catalytic ability of carbon has been recycled about 4 times, I think, during my tenure.
Well, speaking of things being recycled, one that keeps coming back is that catalysis occurs because of a vibration linking the metal catalyst, for example, to the reactant. How did you avoid that?
By being simple-minded. I never did understand that vibration thing very well, and the way I looked at it, there was no, and I still look at it, there's no mystery in catalysis. It's just simple chemistry, the same chemistry you'd get in a beaker, but it has to be done on a surface. There is no magic to it at all, and if you look at what is really the most important achievement in basic catalysis research, it is in the arrival of the understanding of the acidic nature of cracking catalysts. And this indicated that the catalysts were simply strong acids, and the hydrocarbon would react with a strong acid on the surface the same way it would react with a strong acid in the beaker. And when I worked in Washington, I was getting annoyed by the number of proposals that would start out saying these old fogies had no idea what catalysis actually is. We're going to do this and that, and we're going to put catalysis on a scientific basis so that you can actually design catalysts. But if you look back in history, the only real example of designing a catalyst are the cracking catalysts in the petroleum industry. At least they're the most important. And when you see what was done by the petroleum industry as a group of people, they discovered the mechanism of this reaction that involved carbonium ions by just looking at the product distribution. Seeing the nature of the products, they said this looks like something that's been exposed to strong acid and carbonium ions. Then they discovered that these catalyst powders were strong acids. They found that they could control the acidity of the catalyst by varying the silica-alumina ratio. and they control the acidity to get the best results. It's exactly what you'd think of learning the mechanism, learning what the nature of the catalyst surface has to be for this mechanism, and then designing the catalyst to take advantage of this knowledge of the mechanism. So that the concept of scientifically designing a catalyst dates back 30 or 40 years to this one really successful effort. And this effort involves about half of the total catalysis in the world. And because the cracking catalysts are so important compared to other catalysts, so I do get annoyed when people say we're going to do this or that so that we can understand catalysis. And there is no need to understand catalysis. It's just simple chemistry done on surfaces, and because there's such a small part of the total sample is involved, say 1% of a catalyst is really the adsorbed material, it was difficult to get the analytical tools to study what was going on to these surfaces. And this is why the infrared was so valuable. It showed what was going on surfaces, but really it didn't show much that you wouldn't have expected. That if you were an inorganic chemist and you knew that carbon monoxide combines with metals such as nickel to get a carbonyl, you put it on a nickel surface, carbon monoxide, and that's what you got. And essentially everything else on surface chemistry falls within the same analogy type of interpretation. There's extremely few cases where anything different has been found on a surface where the inorganic chemists have not found the same thing before. Now, one of the situations that we encountered was nitrogen on nickel. And we had found that nitrogen adsorbed on nickel, and from the band position, it looked to us that this must be a nitrogen molecule bonded to the surface. And it produced a band, I think it was 2208. Well, in those days, the inorganic chemists did not have any compound in which a nitrogen molecule was bonded to a metal such as nickel. But shortly after we decided by